Welcome to AI for Specialists. We're here to cut through the noise and give you those critical, nuanced insights you need to, well, really get your head around modern AI. Today, it's a deep dive just for you, the specialists. We're looking at AI's inner workings, how it's evolved so fast and what's coming next. We've sifted through a whole stack of sources to basically give you a shortcut to being really well informed without drowning in information.
Yeah, it's a great time to sort of pull back the curtain. For anyone really working with this stuff, understanding the how and the why, it's just crucial, isn't it? We'll look at the concepts that really change the game.
Absolutely. Okay, so let's start with the foundations. You'll know, of course, that AI learning is fundamentally a really complex, high-dimensional optimization problem. We've got artificial neurons, deep neural networks, specialized things like CNNs for images, but what's the actual process? How do they learn?
Well, it's this elegant cycle, really. Prediction and correction, over and over. First, data goes through in a forward pass, makes a prediction. Then a loss function measures how wrong it was, calculates the error. Then comes back propagation. It does clever. It figures out how much each parameter contributed to that error. That gives you a gradient. And that gradient guides gradient descent. You're basically nudging the weights downhill in this complex loss landscape to reduce the error. And a key thing, often missed, is the role of activation functions. They bring in nonlinearity. Without that, networks could only model simple straight-line relationships, not the messy real world.
Right, that nonlinearity is critical. Okay, so that deep learning foundation was setting the stage. And if those loops sound complex, well, things got even more interesting with the transformer architecture back in 2017. You said paradigm shift, moving from processing things one by one sequentially to doing tons in parallel. What was the breakthrough there?
The absolute core of it is the self-attention mechanism. It was genius. See, older models process words in order, right? They struggled if important words were far apart. Self-attention lets the model look at all the other words in the sentence or sequence at the same time when processing just one word. It uses these things called query, key, and value vectors to figure out what's important. Then you have multi-head attention, which lets it look at different kinds of relationship simultaneously. And positional encodings make sure it still knows the word order.
Ah, okay, so it sees the whole picture at once.
Exactly. That parallel capability is what unleashed large language models. It's why we have generators like GPT. Those are decoder only. And models focused on understanding, like BERT, which are encoder only, and others for translation that use both.
It's just incredible how fast this all happened. So you've got the architecture. How do these LLMs actually learn all their stuff and then get, refined?
It's definitely a multi-stage process. Starts with pre-training.
Sure.
That's where it just gobbles up foundational knowledge from massive data sets, hundreds of gigabytes, maybe petabytes of text, code, everything.
Costing billions, right?
Oh yeah, billions for the big ones. And you end up with a really powerful but kind of raw base model. After that comes supervised fine-tuning, or SFT. That's where you teach it to follow instructions using curated examples like question-answer pairs.
So making it useful.
Precisely. But then there's the really tricky part. Alignment with human preferences. Making sure it behaves how we want it to. Historically, that meant RLHF reinforcement malformation. Learning from human feedback. Complex stuff involving humans ranking outputs, trading a separate reward model.
Sounds complicated.
It is. But more recently, we've seen direct preference optimization, or DPO. It's more efficient, directly optimizing based on which outputs humans prefer. It streamlines things quite a bit.
Okay, so you've got this powerful, aligned general model. But how do you make it good at specific things? Like for a particular industry or task, you don't retrain the whole thing, surely.
No, definitely not. The easiest way is prompt engineering. You just use the model's built-in in-context learning. You give it clear instructions, maybe a couple of examples that's zero-shot or few-shot prompting. No changes to the model itself.
Just guiding it.
Exactly.
Right.
But for deeper stuff, or to stop it making things up hallucinations, you use Retrieval-Augmented Generation, RAG. RAG connects the LLM to external knowledge, like your company's database, when it's generating the answer.
Ah, so it looks things up on the fly.
Basically, yes.
Yes.
It retrieves relevant facts, then uses those facts to write its response. Much more grounded, and you can cite sources. And then there's actual fine-tuning, where you do modify the model's weights, training it a bit more on specific data. But even there, techniques like parameter-efficient fine-tuning, PF-LORI is a popular one, let you adapt the model really effectively without the massive cost of full fine-tuning. It makes specialization much more accessible.
Right, PAFT. Good point. Okay, now, The really cutting-edge stuff. Agentic AI, this sounds like a big shift. Not just command response, but delegating tasks, letting the AI figure it out.
Yeah, it's a fundamental change. The AI can autonomously act to achieve complex goals. It's not just answering, it's doing. Think of the LLM as the agent's brain, its cognitive core. It does the planning, breaking down a big goal into smaller steps. It needs memory, too. Short-term, like the current conversation, and long-term, often using vector databases to recall past actions or information.
And it can use tools.
That's the crucial bit. Tool use. LLMs are great at text, but they can't browse the web or do math reliably or run code on their own. So agents use APIs to connect to external tools, search engines, calculators, code interpreters, company databases, whatever they need.
Overcoming the LLM's limits.
Exactly. And frameworks like LangChain or AutoGen help developers build and orchestrate these complex, multi-step agentic systems. It turns the LLM into an active problem solver.
Wow. So with all this accelerating capability, what does it mean for us? What are the big hurdles or challenges we're facing now?
Well, AI alignment and safety are still absolutely paramount. How do we ensure these increasingly powerful systems reliably pursue human values and don't cause harm? The black box nature of some models makes this hard.
The explainability problem.
And then there are the costs,
Yeah.
the sheer computational and environmental costs.
Yeah.
We're talking billions spent annually just training the biggest models. Massive electricity use, huge water consumption for cooling data centers, a significant carbon footprint.
So efficiency is key.
Hugely important. Lots of research is going into making AI more efficient. And finally, there's the big one. The pursuit of artificial general intelligence, AGI. Predictions are all over the place, maybe a 50% chance by 2040, according to some surveys. But the real debate for specialists is, can we get there just by scaling up current architectures like transformers? Or do we need a fundamentally new approach, a completely different paradigm?
Yeah, that scaling debate is intense. It really makes you think about that trilemma, doesn't it? That tension between capability, safety, and cost. If you push hard on capability, does safety suffer? If you prioritize safety, does it slow down progress or increase costs? How do we balance those? It's a huge question for the future.
Absolutely. These are incredibly complex issues, constantly evolving. It definitely encourages all of us to keep exploring and thinking critically.
Well, that's all the time we have today. Until next time on AI for Specialists. Bye-bye.